Over the next several webcasts, we'll be looking at the mechanisms by which enzymes perform their chemistry, and one of the main reasons this is of interest to us is because it'll help us understand the molecular mode of action of drug molecules. The principle behind drug design is one of achieving selective toxicity, the idea that we could kill off an undesirable organism like a bacteria without influencing the health of something that we're interested in, say human beings. Selective toxicity can come about if we can block, by way of a selective inhibitor, these are the drug molecules, enzymes that are essential only to the vitality of that undesirable organism. And in that way we won't interfere with the natural biochemistry of, say, the human being. A classical example of this is the molecule penicillin, which blocks bacteria cell wall construction and therefore limits the growth of bacteria. We're interested as organic chemists in looking at the molecular level details. We really want to understand the organic chemistry behind how this works. And here's a molecule of penicillin, and the way that it works is by mimicking, and that's actually a key word, mimicking the naturally occurring substrate, which in this case is the peptide residue D-ALA, which is important for the cell bacteria wall construction. Basically, penicillin sits in the active site of the enzyme, that's represented by this green trace, and the main bonds and atoms that are of interest are the serine hydroxyl group shown down here. The chemistry that takes place when this beta-lactam structure of penicillin, the four-membered ring, sits in the active site is the steps nucleophile addition to the polarized pi bond, followed by beta elimination and a proton transfer, so that ultimately we've covalently attached the molecule penicillin to the active site and blocking it from doing its further chemistry and constructing a cell wall, and eventually that leads to the death of bacteria. Okay, let's take a step back and look at this picture in a general way, how enzymes catalyze their reactions. To get started with, we'll look at this picture, and this is supposed to be the active site of an enzyme, and X and Y simply represent side chains of amino acids. Those side chains, as we'll see, just like that serine group on the previous slide, are what gets involved in the chemistry. The first step in enzyme catalysis is substrate binding, and the substrate simply fits into the active site and positions itself next to these side chains. So basically, the enzyme serves as a scaffold to position the side chains and to bind the substrate. The next thing that happens is catalysis. Those side chains somehow get involved and convert that substrate into a product. And then the last thing that has to happen is that product needs to be released, and that's known as turnover. So turnover is the process by which we return the enzyme to its original form, and it's ready to begin another catalytic cycle. A typical enzyme active site is shown here. This is the protein tyrosine phosphatase 1b. The enzyme active site, you can see, is actually just a small portion of the enzyme, and that's where the substrate binds. That's where the enzyme side chains that are important in the enzyme's catalytic activity are found. And all of the rest of this, which might be 80% or 90% of the total volume of the protein of the enzyme, is involved really to serve as a scaffold to both house the substrate and position those side chains just where they're needed. Sometimes enzymes recruit cofactors, and so if you had your cornflakes this morning, you achieved basically intake of vitamins that will turn out to be an essential component of some enzyme chemistry. Basically, the way that cofactors work is that they bind to the enzyme active site. Cofactors, as we'll see, carry different chemistry than chemistry associated with the amino acids. And so it's a way to introduce a new functionality that's not found in the 20 naturally occurring amino acid side chains. Once the cofactor is bound, the next thing that happens is the same steps as usual: substrate binding, followed by catalysis, and followed by turnover. Cofactors are essentially metal ions, or they could be organic molecules. Cofactors that are organic molecules are known as coenzymes, and they're the precursors of those coenzymes are really the vitamins that you ingested this morning if you had a bowl of cornflakes. Basically, as I've mentioned, the key point of these cofactors is that they're able to do chemistry that isn't available through the amino acid side chains. And so it's a way for enzymes to recruit chemistry that's not accessible through the natural 20 amino acids.